Hi, welcome to Elephant in the Room. These are short adventures in geography designed to make you think. The idea is, wherever you see this red stamp, I want you to stop and think about what we're doing. These strange rocky mushrooms sitting in the water are called stromatolites. But instead of me going on about how amazing they are, I'd like you to see what you can find out about them. And then you'll be able to answer this question. Why were they so important? So here's a clue. Today we're going to explore geological time. Geological time is full of big scary words like Proterozoic and big strange numbers like 251 million years ago. And this is a shame because geological time tells a really interesting story. How the Earth got to be the way it is. Geologists have pieced it all together like detectives from clues left in rocks, but there is still tons to discover. Having some idea of what happened when and how it all fits together comes in very handy when you're trying to make sense of almost anything about the Earth. But first, we need a little bit of context. So let's start right at the beginning. The Big Bang is thought to have occurred 13.8 billion years ago. Sometimes you'll see giga-annum or GA written, but that means a billion years. So the Big Bang, 13.8 billion years ago. The Sun and the Earth formed about 4.6 billion years ago. The oceans formed very soon after, at about 4.4 billion years ago, and then the first signs of life appear on Earth about 4 billion years ago. So that means that life has been around pretty much the whole time the Earth and the solar system have been in existence. That, in a way, life is a normal part of our solar system. The oxygen-rich atmosphere we animals need, though, has only been around for about 0.6 billion years, and life was busy without it for over 3 billion years before it came along. And here's a scary number. The Sun runs out in 5 billion years. So that means that the Earth and life and the solar system are already entering middle age. The Earth may cool down before that, stopping plate tectonics. So maybe we're even further along than that. Anyway, there's a bit of context. So let's have a look at some of the details. I've got a timeline that's arranged a little bit like a clock face, but you could make one that's just a line. It's up to you. So the Earth forms about 4.6 billion years ago, and the moon breaks off and goes into orbit, and the oceans form, and the earliest signs of life appear about 4 billion years ago. So this is the first phase of Earth's history. The oldest fossils people have found are about 3.5 billion years old, and photosynthesis starts soon after, maybe even at the same time, and photosynthesis produces oxygen as a byproduct, and once that oxygen starts to accumulate in the oceans, that marks the beginning of the Proterozoic. And during the Proterozoic, oxygen concentrations start to build, and towards the end of the Proterozoic, plants colonize the land. And then, at 542 million years ago, strange number alert, that's where there's this explosion of life in the oceans, and this marks the beginning of the Paleozoic. And during the Paleozoic, crustaceans and fish creep onto the land and become land animals, and some of the early trees go completely haywire and form fossil fuel deposits, coal, dragging lots of carbon dioxide out of the atmosphere. And that's followed by the Mesozoic, and that's where dinosaurs are roaming about and flowering plants evolve. And then in the very last phase, grasses appear and the dinosaurs are replaced by megafauna like giant sloths and mammoths and so on. And right at the end of that, just in the last 2 million years, there's this period of glaciations, and right at the end of that, modern humans appear. So that's a basic picture of what's been happening in geological time. So all these geodetectives have pieced all this together by carefully examining clues left in rocks, and the big picture that emerges is a little bit like this. The ocean floor is geologically very young. It forms at mid-ocean ridges and returns to the mantle at subduction zones, forming a sort of conveyor belt that pushes chunks of frothy continental crust about the globe. Continental crust has slowly built up over geological time, and quite a lot of it is older than the ocean floor because it's not being recycled as quickly. Here's some from the Archean, here's some from the Proterozoic, and here's some from the Paleozoic. So, by looking at the right rocks, we can see far back into Earth's history. Much of this continental crust is made of marine sediments which have been scraped up, folded and compressed in collisions between continents, sometimes cooked by volcanic activity. All this is driven by convection currents under the crust in the mantle, fueled by heat building up from radioactive decay deep in the earth and liquefied by the immense pressures. As the surface crust cools, it forms these large, irregular plates, and these jostle about, producing earthquakes and volcanoes along their margins. Now, all this can seem quite distant and abstract, and that's because we're used to thinking of the Earth as a solid thing and we just walk around on it. But actually, the Earth is very dynamic, sort of bubbling away, like when you cook jam, but on a vast scale and over long periods of time. So here's a question for you. How old is that mud on your shoes? You might have to imagine you're from the southwest of the UK for this, but hopefully you'll get the point. The rocks in the southwest of the UK are from a period called the Devonian, about 400 million years ago during the Paleozoic. They were formed by lots of deposition into a shallow sea between two chunks of continental crust we call Gondwana and Euramerica, about 15 degrees south of the equator. And then, during the Permian, at the end of the Paleozoic, these two bits of continental crust collided to form Pangaea, and these sediments were uplifted to form a massive mountain range. Granites from volcanoes were intruded, and the whole thing moved northwards. As this area eroded during the Mesozoic, the granites were exposed, and finally we get to today, about 50 degrees north of the equator, on the edge of places like Dartmoor and Exmoor. So you could say that the mud on your shoes is 400 million years old and comes from 15 degrees south of the equator. 400 million years old sounds really, really old, but actually life has been busy way longer than that. It's been inventing photosynthesis and nutrient cycles, and it's only really recently that our sort of life has appeared. And a significant fraction of the energy that flows through living systems still goes through all that pre-oxygen life, the bacteria and so on, that have been there since the start. And life has been dominating the chemistry in the atmosphere and the oceans all that time. So even things like the mud on your shoes and fossil fuels and the giant insects that produced start to look not so old after all. But it's fair to say, at least from the human point of view, that things really got interesting once oxygen has started accumulating in the atmosphere. And since then, life has been exploring its possibilities and fanning out and generating the fundamental biodiversity we see today. So What started off as photosynthesis in bacteria gives rise to plants and algae and corals, and this eventually culminates in this explosion of life in the oceans, the Cambrian explosion, and that's where crustaceans and insects and worms and the first fish and sharks appear. And then, at the beginning of the Mesozoic, reptiles and amphibians really take off, and they eventually give rise to the dinosaurs. But then there's this enormous asteroid impact in the Yucatan Peninsula in Mexico, so it's thought, and it's bye-bye dinosaurs, hello mammals and birds. And all this has been pieced together by decoding the fossil record. A lot of this biodiversity appears, hangs around for a bit, and then goes again. But some creatures have been super successful. These are horseshoe crabs, but they're not crabs at all. They're distantly related to spiders. They snuffle about in coastal sediments, eating worms and shellfish. They have 10 seriously odd eyes, a tail to flip themselves over. They lay eggs on the beach like turtles, and they have blue blood based on copper instead of iron. Another interesting thing about them is that they're virtually indistinguishable from their fossils, which date back 450 million years. So they've seen continents break apart, coal laid down, the dinosaurs have come and gone, they've been around for much of the time there's been an oxygen-rich atmosphere, and they haven't changed a bit. Why haven't they evolved? Is it because they somehow outcompete everybody else? Or could it be because they're brilliant at adapting their environment to suit what they already are? So there are no environmental messages coming in to tell them that they need to change. Other creatures are much more recent than that. So here we are in the last few million years, and the climate has started oscillating between colder and warmer periods, and this gradually builds up into cold glacial periods and warm interglacial periods like now. And during this time, an ape appears called Australopithecus. And this is an ape who walks on 2 feet and uses stone tools and fire, and one of them is the famous Lucy skeleton from East Africa. And as the climate becomes more variable, another ape appears, and this is Homo erectus, the Neanderthals, and right at the last minute, Homo sapiens. And they evolved in East Africa about 200,000 years ago. They spread out from Africa about 100,000 years ago. They were in Asia by 75,000 years ago, in Australia by 50,000 years ago, and right at the peak of the last glaciation, when sea levels had dropped by a whopping 200 meters, they crossed the land bridge, or there's recent evidence that they may have taken boats across the Pacific into the Americas. Modern human populations began slowly growing when the Earth suddenly warmed about 12,000 years ago, allowing agriculture to develop. But they positively exploded in just the last 100 years or so, and it's really thanks to the fossil fuels life laid down 300 million years earlier. So here's an interesting question. Are humans somehow trying to adapt their environment to suit themselves too? See if you can think of a way that they are, and then explain how that thing is going to help them to be as successful as horseshoe crabs. Okay, so there we are. That's one route through geological time, and there are a gazillion others, of course. One way that scientists often try to make sense of the Earth is by comparing it to Venus. Venus was made of similar amounts of the same material in the same region of the solar system and at the same time as Earth, but it went in a very different direction. It has a 96% carbon dioxide atmosphere from a runaway greenhouse effect, and the surface temperature is about 480 degrees C, hot enough to melt some metals. It rains sulfuric acid, the air is about 100 times thicker than on Earth, and because there's no water left to help disperse heat, there's not even any plate tectonics. So here's my final question. Did Earth just happen to be a good place for life? Or did life make it that way? Maybe the Perseverance rover on Mars at the moment will shed some interesting light on this. Who knows? So, thanks for listening, and see you next time.